So in this lecture, we're going to revisit multiplication. So if you recall, we looked at the classical lattice multiplication algorithm in the first lecture. And it's also in the first chapter of Jeff's book. And this is just the classical algorithm you've probably used throughout your life, where you do shifts and adds. But now the question is, we know this algorithm is O of n squared, so can we do better than that? That's the question. So to do this, we're going to exploit some identities of numbers. So consider some digit sequence like this. And in particular, let's forget the 1 because we want this to be even number of digits. So just based on how 10-digit system works, we can actually write this as the number 9876 with 4 zeros plus the number 4532. So essentially, we can split these numbers in the middle and then independently play with both sides. So in other words, we can write it in the form 10 to the m times a plus b, where a and b are m over 2 digit numbers. Actually, a and b are both m digits. And overall, this will be a 2m digit number. And we'll call n 2m. So that's one way to split up the number. And so since we're thinking recursively, we might want to exploit this to multiply two numbers. So maybe we have two numbers x and y that we want to multiply. And we're going to assume these are both n digits. So the first thing we could do, instead of multiplying them directly, is consider the expanded forms, 10 to the m times a plus b, and 10 to the m c plus d of x and y. This one's x. This one's y. Okay, so we can do this out just by using foiling, basically. And what we can get is this will be 10 to the 2m times a c plus 10 to the m times bc plus 80, and then plus BD. And what's the benefit of this? Well, each of these numbers are, or each subpart, are going to be m digits, where m is n over 2. So we've simplified our problem from multiplying two n-digit numbers into multiplying two n divided by 2-digit numbers. So smaller multiplications. And so we can compute these recursively. So the idea would be we can recursively, specifically, compute a times c, b times c, a times d, and b times d. We can also add any numbers we need to. And this is more efficient. This takes only O of n time instead of O of n squared. And then we can also do shifts. So shifts are equivalent to multiplying by 10 to some power. So here, say 10 to the 2m, or 10 to the m. So multiplying by 10 is easier than general multiplying because you essentially just slap zeros on the end of the number. So i.e., you're slapping zeros on the end of the number. And so this is, of course, still O of n time to do. So this seems like it could give us some savings. Instead of multiplying the numbers, we focus more on adding them and doing shifts. So overall, what would this algorithm give us? Well, the recurrence, t of n, this would be 4 subproblems because of 4 multiplications. Each one is roughly size n over 2. And then we do outside work, a constant number of linear time operations, which are the shifts and the additions. So let's try using the recursion tree method, to expand on this recurrence. So at the top level, we have an instance of size n, and overall we do linear work, doing the additions, then we spawn children of size n over 2. There's going to be 4 of them. So this will be 4 times n over 2, which is 2n. The next layer also will have 4 children per node. And so you're going to get a lot of nodes here, 16 in total. So you have 16 total nodes, each takes n over 4 time, and so we have in total 4n. And the pattern is going to continue. Each time we'll have a factor of 2 to the current level times n, where L is the current level. Okay. Now the total height of this tree, capital L, this is going to be log base 2 of n. That's because we need to divide n by 2 each time. And the base case of our process will happen, say, when we have 1 digit or 2 digits, some constant. So overall, the height will be roughly log base 2 of n. So overall, the running time, t of n, would be the sum from I equals 0 to log base 2 of n minus 1 of 2 to the I times n. And we can use a formula for geometric series. So the formula says the sum from I equals 0 to n of r to the I is r to the n plus 1 minus 1 divided by r minus 1. So if we plug this in with 2, we get n times 2 to the log base 2 of n minus 1 over 2 minus 1, which is going to be exactly n times n minus 1, which is clearly O of n squared. So it's no better than lattice. We really haven't made any savings in time here. Although the algorithm is correct and does use a different approach, we haven't achieved our goal. But Karatsuba who invented this algorithm, made a simple observation, which is the following identity. The identity says that AC plus BD minus A minus B times C minus D equals BC plus AD. So how does this help us? This allows us to remove one multiplication. Otherwise known as a subproblem. So how does it do this? Well, instead of having these two multiplications, we already have to compute these two multiplications anyway. So we already have to do these two multiplications. So now all we have to do is one more, which is multiplying these two numbers. So overall, we just have 3 multiplications. Now the downside, of course, is we have more additions and subtractions, but that just jumps into the O of n in the recurrence. So the running time of this algorithm, which is the fast multiply algorithm in the textbook, is going to be exactly T of n is 3 T of n over 2 plus O of n. So we could use the recursion tree method again, it'll work out exactly as before, or we could just apply the master theorem directly and note this is the increasing case. So in particular, that means the solution T of n is O of n to the log base 2 of 3. The 2 is coming from the fact that we're dividing n by 2, and the 3 comes from the fact that we have 3 subproblems per step in the recursion. And overall, this log base 2 of 3 is something like O of n to the 1.58, which beats n squared. So this algorithm beats what we had before. Now, we again want to think about correctness. So what's the correctness argument? Well, here it's easy because we're just using an identity of an algebraic identity. So we know by definition that x times y equals this thing. That expression above. So as long as we're correctly multiplying and adding things, the whole algorithm's correct. In particular, assuming we're using a correct addition plus and minus algorithm, those steps are correct. Which we can always assume we know how to add and subtract. So then the only other step is to compute the smaller multiplications, and the smaller ones we know are correct by the induction hypothesis. In other words, the recursion fairy computes the smaller multiplications for us, and then we just have to combine them using pluses and minuses, which we know how to do. So the overall algorithm is correct. And the same kind of strategy also applies in other algorithms such as matrix multiplication,